Good morning, good afternoon everyone, and welcome to this Unity tutorial on how to create a simple behavior tree in less than 30 minutes. In this episode, we're going to implement a very simple guard AI using behavior trees to have it patrol or target and attack monsters. Are you ready? Then let's dive in. In a previous video, I talked about finite state machines, aka FSMs, and I discussed how this pattern can help you implement well-organized and well-structured behavior systems, as long as this behavior isn't too complex. In a follow-up episode, we saw how hierarchical finite state machines can mitigate some of the downsides of the FSMs by introducing inheritance and higher-order abstract states. But the fact is that when you try and model a more complex behavior, FSMs will eventually come short. Chances are that if you work on a really advanced AI system, or just on a player system that offers more options to the player, FSMs will be too rigid a structure to be pleasant to use as developers. Now, of course, you can always manage to cram up all of your super AI in an FSM, but trust me, it will soon be a real pain to maintain, verify, and update. So another common AI pattern that is way more flexible is the behavior tree. Here, rather than defining a finite set of states that your character can transition between, you define a tree of nodes that altogether create branches with various behaviors. Each node has an execution state that determines whether it's currently running, if it's succeeded, or if it's failed. This state is computed by evaluating the node, thanks to a function that's naturally called evaluate. The state of the branches is then computed from the state of the children nodes and aggregated in various ways depending on this parent node type. The nodes at the very bottom that have no children are called leaves. And those leaves are going to contain the actual checks and tasks that are performed by our AI, while the rest of the tree is the logic structure that's going to essentially switch from one behavior branch to another. In other words, the inner nodes control the flow, and the leaves ultimately implement the actions. The flow control nodes in the middle define how the tree is processed. They can be of two types. Those structure nodes can be composites. So those nodes are sequences that have a bunch of child nodes that they run in predetermined or random order, one after the other or in parallel. Usually they act like an AND or an OR logical gate, for example. Or else those structure nodes can also be decorators. In that case, they have a single child and they may impact its processing or modify its results before returning, like reversing the failure success state, delaying the execution, and so on. Action nodes are more diverse, but you can usually group them in two categories: the checks and the tasks. Checks are simple if-like nodes that condition whether or not this branch is valid and should continue. Tasks are more complex nodes that perform a real update of the character or its environment. Something really nice with behavior trees is that prioritizing actions is easy. Because the success of the child nodes conditions how the branch and therefore the tree runs, combining composite ANDs and ORs can directly give you a set of prioritized features. Behavior trees natively handle sequences, interruptions, and fallbacks. Also, as you can see, this structure is pretty easy to read and to visualize. You just follow the branches by priority and at each node check whether it succeeds or not to know if you can continue on this branch or if you must go to the next one. But the biggest advantage of behavior trees is that they are highly modular and scalable. By removing or adding a branch, you essentially add or remove a feature to your character. Similarly, it's pretty simple to copy a sub-branch and paste it somewhere else to just copy-paste part of your behavior. Some subtrees can even be completely self-contained autonomous bits of logic that you can then re-import and reuse in another character's behavior tree to quickly implement chunks of a system, like following a target, patrolling between a set of points, etc. Moreover, this modularity means that you can build your tree piece by piece and have an incremental design strategy. Finally, note that contrary to finite state machines, where by definition states are as isolated from each other as possible, behavior trees are far more flexible to leaking information between nodes. Even though each node is executed on its own and lives its own life, it is pretty common to have some shared data state that can be accessed from various points in your tree to have global, although context-specific variables. But enough talking. Let's get to actually coding a behavior tree so that we better understand how it works. In this tutorial, we will create a basic AI for this guard. By the end of the session, it will be able to patrol between a set of points when idle, keep an eye out for monsters like this skeleton, and go to them if one is nearby to finally attack until the monster is dead. We'll focus on the guards, so the enemy won't do anything, but of course the techniques we'll learn here can be applied for any unit, so you could easily transpose what we're gonna do to another AI system for the skeleton. For this tutorial, I'll be using various free assets from the asset store or from online texture databases. You can check out all the links in the description for more info. And I won't go into the details of how I made this 3D scene, but if you're interested, be sure to let me know in the comments, and I might make another video on this topic. Okay, so let's assume you have your 3D scene designed, populated and ready. In here I have my guard, the skeleton near a campfire with a simple particle system, and a few crates and lights for the ambience. The guard has a basic animator that has 3 possible states: idle, walking and attacking. Each state has its own animation, and the transitions between those animator states are controlled by 2 Boolean variables: walking and attacking. The skeleton just has a single animation in its animator, an idle animation. It has a box collider, and it is on a user custom layer for the physics that's called enemy. This physics layer will help optimize the checks for nearby enemy units in our code. Part of my behavior tree will also reuse the simple patrolling system I talked about in this other tutorial. So I've prepared a few empty game objects to act as waypoints from our patrol route, and if you want to learn exactly how this system works, be sure to check out this episode. I'll put the link in the description of this video as well. Now it's time to dive into the programming of our behavior tree. To implement the behavior tree, we will work in 2 phases. First, we'll define some generic architecture that could be used by any behavior tree, along with a few composite nodes. And then we'll focus more specifically on our guard and design its particular behavior tree structure and the nodes inside it. So first, let's prepare our generic behavior tree architecture. To begin with, we'll work on our atomic element, the node. Let's create a new script folder called behavior tree, and inside it create a new C# script, node.cs. Open it in your editor and remove the default Unity start, update and mono behavior. To make this tool more reusable, I declare my generic classes inside a behavior tree namespace. This way, I will just be able to use it and include it anywhere I want in any project. Now, our node class will be a basic C# class that represents a single element in the tree and can access both its children and its parents, has a node state that uses an enum, and can store, retrieve or clear shared data. Let's start with the state. We need an enum with 3 possible values: running, success or failure. Then, in the class, we'll declare a state for the node using this enum. We'll make it protected so that classes that derive from this node class can access and modify this value. Similarly, we can make a public parent variable and a protected list of children. Having a link in both directions is interesting because it will make it easier to create our composite nodes by looking at the children and to have shared data by looking at the parents and backtracking in the branch. These children will be assigned in the constructor of the class, or else they'll just be empty. So by default, the empty constructor will simply assign a null parent node. And then, to be sure we properly link the parent field when we create our tree, we'll rely on a util method called attach that properly creates the edge between a node and its new child, and we'll call this from the node constructor like this. Now we can prepare the prototype of the evaluate function. It will be virtual so that each derived node class can implement its own evaluation function and have a unique role in the behavior tree. To finish up our node class, we need to take care of the shared data. So this data will be stored in a dictionary of string object pairs. By using the C# object lazy type, we essentially have a mapping of named variables with the string that can be of any type and that is therefore pretty agnostic to the data you want to store. So to set the data, we just need to add a key in this dictionary. To get it back, it's a bit more complex because we want to check if it's defined somewhere in our branch, not just in this particular node. This will make it easier to access and use shared data in our behavior tree. To do this, we'll make the getData function recursive and continue working up the branch until we've either found the key we were looking for or we've reached the root of the tree. To clear data, the process is pretty much the same. We recursively search for the key, and if we find it, we remove it, or else, if we reach the root, we just ignore the request. Okay, now that we have a node class, we can go ahead and implement the second core object of our package, the tree class. This other C# script will be a mono behavior, and it will contain a reference to a root, that is a node that itself recursively contains the entire tree. And then it just needs to do two things. First, upon start, the tree class will build the behavior tree according to the setup tree function we defined, and then in the update, if it has a tree, it will evaluate it continuously. Finally, to end this first part on the implementation of a generic behavior tree, let's prepare two composite nodes, the sequence and the selector. The sequence is a composite that acts like an AND logic gate. Only if all child node succeeds will it succeed itself. To implement it, we just have to derive from the node class and override its evaluate method. Then, in our overridden evaluation function, we will iterate through the children and check their state after evaluation. If any child fails, then we can stop there and return a failed state too. Else, we need to keep on processing the children and eventually check if some are running and therefore block us in the running state too, or if all have succeeded. The selector node, on the other hand, is like an OR logic gate. It's almost the same code as the sequence, except that we return early when a child has succeeded or is running. Okay, we now have a toolbox for our behavior trees that will make it easier to create our own specific AI system for this guard. We will build this custom tree gradually and add more action as we progress. So our very first behavior tree will be real simple. It will have only one node, the task patrol node. There won't be any internal node for flow control because for now the guard will always execute the same action, patrolling. This node will be executed continuously and it will re-implement the basic patrolling algorithm that we saw in this other tutorial. First, in another script subfolder, let's create a new C# class called task patrol. Import our behavior tree package and have task patrol inherit from the node class. Again, we want to override the evaluate function, but also the constructor. That's because our patrolling algorithm needs a few additional info, like the waypoints to use, but also a reference to the transform of the agent performing this action. Since task patrol is not a mono behavior, but a somewhat abstract blob of data, we need to pass it the transform to use. We will store these variables in the class as private members and then simply copy back the code we had in the patrolling tutorial. In my evaluate function, I need to update and return the state of my evaluation function depending on where it's at. This node will just be running continuously again and again, so I'll just put this at the end of the method. Then I replace the few missing variables with their new equivalent, so instead of the transform, I'll use underscore transform and some things for the waypoints. For the speed, I'd like this to be defined at a higher level so that all nodes in my tree that need this variable can find it and share it easily. So I'll just make it a public static float in my behavior tree class itself. So the behavior tree will be defined in a guard BT C# class that inherits from our tree class. And this is where we'll expose a public field for the waypoints that will then pass on to the task patrol node, where we'll set our global speed variable to reuse in the task patrol evaluate function, and where we'll define the actual structure of our tree in the setup tree method. For now, this tree is just a single route that uses our new task patrol class. If I put this component on my guard and assign the waypoints, you see that when I run the game, the guard now goes from one waypoint to the other with a little wait at each, just like in the patrolling tutorial. Of course, we'd like for the model to use its walk animation in between the waypoints. So let's go back to our task patrol, and when we get the transform, we'll also get a reference to the animator on the same object. Then, in the evaluate function, we'll set the walking boolean to true or false when we finish waiting or when we reach a new waypoint. And ta-da! The guard now walks through its patrol path. Okay, now let's ramp things up a little and add some behavior to spot nearby enemies and go to a target once it's been defined. This time, this action will require two nodes. First, a check enemy in FOV range that returns a success if there is at least one enemy close by in the field of vision radius, and a failure otherwise. And then a task go to target that moves the guard towards the target that has been found. These actions will be inside a sequence because we only want to move to a target if we did spot one. And overall, we'll want either this sequence or the basic task patrol to be used. So we'll need a new selector node as the root to link those two little branches together. To keep a reference to the target enemy, we'll use our shared data system. The check enemy in FOV range node, if it finds an enemy, will store this target in the root of the tree so that the task go to target node, and perhaps other nodes later on, can retrieve it and use it in its computation. So this new class will again inherit from the node class. It will require the transform in its constructor. And in the overridden evaluate function, we'll check to see if we already have a target by using getData. If we have one, then we succeed automatically. Else, we need to do a little check of our surroundings using something like Unity's physics.overlapSphere that returns all the colliders that are found inside the sphere around a given position. We'll limit this search to just the enemy layer, take our position as the center of the sphere, and define a new static variable in the tree, the FOV range, that we'll use here. Then, if we did find at least one collider, we'll store the first collider in our list in the target slot of our shared data, in the root, which is 2 levels above, so this is why I use parent.parent. And we'll also return a success. Else, we'll fail on this node and stop the processing of this branch there. Just to be explicit, we can also make sure that the walk animation is playing by getting a reference to our animator and setting the walking boolean to true. The task go to target class is pretty straightforward to code based on the previous node we prepared. We just get our transform, try and get the target from the target data slot, and if we have one, move towards it. And we just return a continuous running state. To finish this up, let's use our new node in the guard.bt script. So we'll replace our root with a selector and pass in 2 children. First, the sequence with the check and the move task, and then our task patrol node from before. Remember that the order in here is important. This is what gives the list of priorities for your actions, and so in our case, this sets the patrolling as the fallback action. If you run the game again, you'll see that now, when the guard gets close enough from the enemy, it will interrupt its patrol and move towards the target. The last thing you want to implement is a basic attack behavior. So when the guard gets real close to an enemy and this enemy enters its attack range, the guard should switch to attack mode and regularly deal some damage to the enemy. Again, we won't have the enemy react in any way in this tutorial, but you could easily use the same techniques to create a behavior tree for this unit too. The attack sequence will be pretty similar to the targeting one. We'll have a check node for the attack range and then a task node for actually attacking. However, we'll assume that the target has already been found and filled in when we try to attack, so the check enemy in attack range routine will not look for colliders. It will just check the target shared data slot. So if it doesn't find a target, it just fails. Else, if the enemy is close enough, it will succeed. We'll also want to change the guard animation to the attack animation, so I'll take my animator and set the attacking flag to true and the walking flag to false. Now, the task attack class will need a reference to the enemy's enemy manager component so that it can lower its health points. This script I won't talk about here, but you can check it out in the GitHub repo that's linked in the description of this video if you want to see what the script looks like. And it's basically just something that defines some initial health points pool for the enemy and then lowers it by a fixed amount every time it receives a hit. Then when these health points reach 0, the enemy dies and it just disappears. So to get this component, we'll be using getComponent, but because getComponent is not efficient, it's better to cache this result for as long as my target stays the same. So I'll just have a reference to my target and a reference to its enemy manager. And if I have the same target, I don't have to recompute it. Otherwise, I'll just use the getComponent. Then I'll just have a little counter, just like in my task patrol, to attack every second. And so the take-hit method from my enemy manager script returns a boolean that tells me if this blow was the final one and if the enemy is now dead. So in that case, if the enemy has died, I want to clear my target's data slot and switch back to walking to return to my normal patrol path. So by clearing the data, we basically make sure that all the check nodes that were true up till now are now false, and that will reset to the fallback behavior we had at the very beginning. We can add this new branch in our tree at the very top of the list so that it has the highest priority. And if we run this, we see that now the guard patrols, then spots the enemy when it enters its FOV range, moves towards it, and then it will attack until the skeleton is down, so until it has taken 3 hits, and finally the guard will just resume patrolling as its fallback behavior. That's it for today, folks. In this tutorial, we saw what behavior trees are and why they can be better than finite state machines for complex systems. We then created a basic AI for our little guard so that it is able to patrol and target or attack enemies. This was a very short introduction to the behavior tree AI pattern. Of course, if you're time constrained or you'd rather look into ready-made solutions, there are plenty of packages in the Unity Asset Store for this feature. Most notably, the Observe Behavior Tree system that is really great and has an intuitive, user-friendly, graph-based editor. Don't hesitate to post comments with your ideas on how to improve and experiment with this feature. And in the meantime, feel free to like and share this video or to subscribe to my channel so you know as soon as new videos come out. Thanks for watching and take care.